So how is the oscillation getting started? So you know that we are going to use a common emitter amplifier for our designing oscillator. So emitter is grounded. So input is going to be base, output is going to be collector. So when you don't give any AC signal to the base, you give only the biasing supply to the collector. So you have a lot of electrons in the base which start moving randomly. You know, when electrons move randomly, they generate noise. And even a small variation in DC power supply will also generate noise. So these noise components will be extremely small. They will be in the order of microvolt or microamperes. And they are always present in a semiconductor. You cannot have a semiconductor which is completely free of noise. So these noise components are present at the base. When the DC power supply is switched on, these noises enter the base and come out of collector. No external signal is applied. These noises will act as input to the amplifier. So the output of amplifier will be the amplified version of noise. And that output is again taken and fed back to your input as input again in the base. And you know that these amplifiers will work only at one particular frequency, if not. So the output signal will be only at this frequency. So whatever noise generally will cover the entire frequency, right? So, but since your circuit is going to work only one particular frequency, the output at that particular frequency, the noise at that particular frequency alone will be dominant. The other noise signals will be filtered out by your amplifier. So this output amplified version of noise output is taken from the collector and it is again fed back to the base in phase. That is the property of positive feedback. In positive feedback, the feedback signal and the input signal are in phase. Only then you can expect the device to have positive feedback. So the output slowly increases, the feedback also will increase, the input will increase. So this process continues and the output goes on increasing. But as the signal level increases, so you know that the gain of the amplifier is going to be 1 by beta. So the gain of the amplifier is going to be 1 by beta. So as the feedback signal is going to increase, the gain of the amplifier will start reducing. So the gain of the amplifier will start reducing because gain A is approximately equal to 1 by beta. Okay, so A is approximately equal to 1 by beta. The frequency at which the output voltage remains constant is called frequency of oscillations. And the essential condition which are to be considered, the essential conditions which are to be considered for maintaining oscillations, these two conditions, you know, it is very, very simple. You have already studied them. It is called as Barkhausen condition for sustained oscillations. Modulus of A beta should be equal to 1. So A, you know, it is the open loop gain of your amplifier. Beta is the feedback fraction. So modulus of A beta equal to 1. So the magnitude of loop gain must be unity. And the total phase shift around the loop should be 360 degrees or 0 degrees. If these two conditions are satisfied, then you will get sustained oscillations from the amplifier. So your amplifier will no longer amplify your signal. In turn, it will be generating as a source of potential oscillations. Okay. So this is how your oscillations start growing up in your amplifier. At one stage, your oscillations cannot grow beyond a particular range because your device will limit that. So that that at that point, the output voltage remains constant. And the output frequency, if you measure, that is called as the frequency of oscillation.